Okay, a student finds it takes 0.2 seconds for a ball to pass through the photo gates placed 30 centimeters apart on a level ramp. The end of the ramp is 92 centimeters above the floor. Where could a coin be placed so the ball directly strikes the coin on impact with the ground? So we've got this situation where there's a ball that rolls off the edge of the ramp, hits the ground. We need to figure out how far away from the table that is. So that's our change in horizontal displacement. We need to know what our velocity is when we come off this table. And so to figure that out, we need to use the information about how the ball goes through the photo gate. I always convert things from centimeters to meters because acceleration due to gravity is in meters per second. And so since that's what our constant is, I like to just use it as it is instead of try to rearrange it. So this is actually going to be 0.3 meters of distance. To figure out this velocity, what we need to do is look at our change in distance divided by our change in time, and that is just a rearrangement of our one horizontal equation for this unit. So, see, 0.3 meters divided by 0.2 seconds is going to give us 1.5 meters per second. And so now we know all of the we know some of the horizontal things. So this right here has nothing to do with this thing solving the problem below except for that velocity. We need to make sure that we keep track of our vertical variables and our horizontal variables because we don't want to use them interchangeably in those equations. So I usually make two lists and I label one vertical and one horizontal. You can label them vert and horiz. You can label them v and h. You can label them y and x. It doesn't matter. They're just names. So the things that we know. We know that in vertical things that our displacement, our change in height is going to be minus 0.92 meters. It was 92 centimeters, but if we need to convert it to meters, that's what we would need to do. And it's negative because we're going downward. We know that our initial vertical velocity, so there's going to be a velocity downward, our initial vertical velocity is 0 meters per second, just like if we were dropping something, rock or baseball or whatever. We also know that our acceleration due to gravity is minus 10 meters per second squared. So we know three things, which is good because we know that with our equations, all of them have four variables. So if we know three things, we can always solve for the fourth. For horizontal stuff, we're trying to find our horizontal displacement, and we know that our velocity is going to be 1.5 meters per second because that's what we calculated up on the top. We're trying to find the distance, so that tells us that we really need to know the time, but we don't. So luckily, we can solve for that using our vertical variables. So we need an equation that accounts for our displacement, initial velocity, acceleration, and time. And the one to use is going to be this one in the middle. This is not corrected yet. It's going to be times t. So I'm just going to rewrite that. Change y equals 1/2 a t squared plus vit. Lucky for us, because I don't like to solve quadratics, is that our initial velocity is 0. So this whole term becomes 0, and we don't have to really worry about it. Yay! So to solve for time, our displacement is going to be minus 0.92 meters. We set equal to 1/2 times minus 10 meters per second squared times time squared. Let's simplify this a little bit. 0.92 meters equals minus 5 meters per second squared times time squared. And then if we divide both sides by 5, we find that time squared is equal to 0.184 seconds squared. Time, of course, is the square root of that. And we find that time is 0.43 seconds. How'd you guys do? Got it? Yay. But that's not the end of our problem. So we had 0.43 seconds. And we can use that down here. So our horizontal displacement is going to be velocity times time. Velocity was 1.5 meters per second. Our time is 0.43 seconds. So our total here is going to be 0.64 meters. So this point is going to be 64 centimeters or 0.64 meters. You guys have any questions about that? So far, so good. Okay. So next, it's a suppose now that the same ball released from the same ramp struck a coin in the floor placed 25 centimeters from the end of the ramp. Is that closer to the table or farther away? If this is 64 centimeters, and now we're going to go 25. We're going to be closer to the table. Right, so now the ball is going to come off the ramp and land closer to the table. Do you think the ball's going faster or slower? Slower. I think so too. So we'll test that. First, it says, what was the ball's horizontal velocity? Well, let's see. Horizontal stuff. So we know how much time it takes to get to the bottom because none of the things in this equation change just because the distance away from the table is different. Our height is still the same, acceleration is still the same, initial velocity is still the same. So it makes sense that time would be the same. So we know that our time is equal to 0.43 seconds. I'm going to put that down here too in a vertical section. To figure out the horizontal velocity, that's what we want to know, we're going to have to use our change in x. So our change in x now is 0.25 meters. So to figure out our velocity is going to be our change in distance divided by our change in time. So this is going to be 0.25 meters divided by 0.43 seconds. And that's going to give us a time of, let's see if I got this right. A little gun check because I think this is where I screwed up before. 0.25 divided by 0.43. And I got 0.58 meters per second. So that's how fast our marble or our ball was traveling when it came off the side. We said that we thought that that would be slower. Is that slower than before? Before our horizontal velocity was 1.5 and now it's 0.58. So it's a lot smaller. Next it says, how long did it take the ball to pass through the photo gates? So this is a different sort of issue, right? Our photo gates are, I should bring some in to show you guys. We have some upstairs. They're like little arches that you put over a path, and then when the ball goes through the path, it measures how far it takes. We know that these guys are 30 centimeters apart. So that's equal to 0.3 meters. And we know the velocity. And so if we want to figure out the amount of time, we can use the same equation. Only we're going to solve for time. So time is going to be equal to our change in position divided by our velocity. Our change in position here is going to be 0.3 meters divided by our velocity, 0.58 meters per second. We're going to end up with 0.52 seconds. So it's going to take more time for it to go through. Before, remember, it took 0.2 seconds. Now it's taking 0.5. So it takes more than twice as long for them to go through the photo gates. You guys have any questions about 2 and 3? No? All right, I want to talk a little bit about number 1. Oh, it's okay. This is a real movie called The Gods Must Be Crazy, and it's about a bunch of people who had never seen modern civilization before, and all of a sudden stuff like airplanes are flying overhead. You can imagine how alarming that would be if you were not used to seeing airplanes. So I'm going to draw a picture of what we have first. So there, I'm going to put my airplane up here. Oh, my tail is kind of big there. Whatever. Okay, so there's my airplane, and it's going to drop a bottle that falls over here. And so our path is going to look something like this. Doing okay so far? How are you guys doing? You guys are less chatty than you started out the day. All right, so our bottle is going to travel. Well, I guess we can read this. The movie, The Gods Must Be Crazy, begins with a pilot dropping a bottle out of an airplane. A surprised native below, there's our native, who thinks it's a message from the gods, recovers it. If the plane from which the bottle was dropped was flying at a height of 500 meters, 500 meters, and the bottle lands 400 meters horizontally from the initial dropping point, how fast was the plane flying when the bottle was released? So what we're trying to find here is a horizontal velocity. That's what we don't know. We do know our change in horizontal position is going to be 400 meters. Do we know the time that it takes for it to fall? We don't know the time yet. Don't know. Vertical stuff that we know. We know that when it's dropped, the initial velocity is 0 meters per second. We know that the acceleration is minus 10 meters per second squared. We also know that this thing falls a distance of 500 meters. So I'm going to say our displacement is minus 500 meters. Can we solve for time with that information? We can, because we have three things. In fact, the equation we're going to use is that one that's parabolic that we've used before. Change in y equals velocity times time plus 1/2 times acceleration times time squared. And because our initial velocity is 0, we're not going to have to worry about that first term. So we know then that our displacement minus 500 meters is equal to 1/2 times minus 10 meters per second squared times time squared. Minus 500 meters equals minus 5 times t squared. T squared equals meters per second squared. T squared equals 100. Sorry, seconds squared. So time is equal to the square root of 100 squared, s squared, or 10 seconds. So we know time is 10 seconds. We can put that over here. And if we know the time and the distance, we can figure out velocity, because velocity is the change in position divided by the change in time. So our change in position is 400 meters. Our time is 10 seconds. So this is going to be 40 meters per second. You guys have any questions? I think I'm going to save the motion map for tomorrow. What was that?